The last lecture was on a two-layered system. Now we will focus on a three-layered system. So what we will do is we will take a three-layered system and solve it in a Kenpave and find out what is critical stresses and strain at a critical locations, at least two different critical locations. One is at the bottom of an asphalt layer and second one is at the top of a subgrade layer. So we will directly move into the numerical. So you have a three-layer structure, something like this. This is subjected to a single V load and with the contact radius of 122 millimeter and a contact pressure of 828 kilopascal. So this load is acting on a structure with three-layer system. The surface layer has a thickness of 152 millimeter and base layer has a thickness of again 6 inch, which is 152 millimeter. Yeah, and the bottom layer is of an infinite thickness. The modulus of each layers are as given here. First layer modulus is 2.8 gigapascal. Second layer modulus is 138 megapascal. And third layer modulus is 69 megapascal. Let us find stresses and strain at two critical locations. One is at the bottom of an asphalt layer and second one is at the top of a subgrade layers. We will find out all the components of stresses and strain and we will see how these values varies. So these are the inputs we need to give in a Kenlayer for solving this numerical. So in the general information, so you have type of material to be linear, low damage analysis, number of period is 1, load group is 1, which is single axial, single wheel. Let us keep the numerical integration tolerance to be as a default value. Here the number of layers is 3 and number of z coordinates we are looking for the analysis is 2. One is at the bottom of top layer and second is at the top of a subgrade layer. So other values we will just keep it as a previous one and we will use a SI system here. So once you complete your general input, so these are the layer thickness and Poisson's ratio property. Top layer is 6 inch thickness, which is 15.2 centimeters. Second layer is also 6 inch thickness, 15.2 millimeters. Bottom layer is infinite thickness. So let us use a Poisson's ratio of 0.35 for a surface layer and base layer. If you want, you can modify it and check how the value varies. The subgrade Poisson's ratio, I will keep it as 0.5. So for these values, your z coordinates, we have given two z coordinates. So the first z coordinate is going to be 15.2 centimeter and the second z coordinate is going to be the bottom of an second layer, which is going to be 15.2 plus 15.2, that is 30.4 centimeters. So with this z coordinates, we will find out stresses and strain at 2 points. Now these are the modulus value for three different layers. So you can see that the top layer has a maximum modulus and the subgrade has a minimum modulus. So once you complete the modulus input, this is the load information which you have to give. 0 for single axial, single V, contact radius is 12.2 centimeter, contact pressure is 828. Since it's a single axial, single wheel, YW and XW values are 0. Let us keep only one radial distance here, so which is at the center of loading. So you have a load here, RC is 0 at this point, so you use center of loading. So now once you give all this input and compile it, this is the result you will get it. So we have given only one radial distance, which is exactly at the center of loading, so along this axis. So we have given two vertical coordinates, which is 15.2 centimeter, this point, and 30.4 centimeters is this point. So the first line results corresponds to the bottom of an asphalt layer. The second line results corresponds to the top of a subgrade layer. These are the critical stresses and strain at two different depths. Now, the vertical stress and strain at the top of a subgrade layer, that is at the depth of 30.4 centimeter from the surface, that is 51.065 and 5.466 E minus 4. This is going to govern the rutting in subgrade layer. And tensile strain maximum, which is minus 3.142 E minus 4, or the corresponding stress, this value is going to influence a fatigue damage in asphalt layer. So these are the critical stresses and strain we will be using further in the design. Now we will see how the thickness of a base course influences tensile strain at the bottom of the asphalt layer. So for this purpose, what we will do is we will use the base course thickness of 8 inch. In previous case we used 6 inch. Now we will use 8 inch and determine tensile strain at the bottom of an asphalt layer, and we will check how this thickness of a base course influences the tensile strain value. So we have to solve one more Kenlayer analysis here with the base layer thickness of 8 inch. So these are the input for that purpose. General information will remain same as our previous information. Modulus value same as our previous information. Load value is also same as our previous numerical here. The only variation is with the layer thickness. First layer is of 6 inch thickness, 15.2 centimeter. Second layer is of 8 inch thickness, which is 20.4 centimeter. The Poisson's ratio value is same as our previous numerical. Since thickness are varying, interface distance from the surface will also vary, that is Z coordinate system. So first is at the interface of first layer and second layer, which is 15.2 centimeter. Second is at the interface of second and third layer. So it is 15.2 plus 20.4, which is 35.6 centimeters. Now we will give this as an input and compile the Kenlayer program, and this is the result which you will get it for 35.6 centimeter Z coordinate. So we are interested in finding what is the tensile strain at the bottom of asphalt layer, which is this value. In the previous case, it was this. So when you compare, the values are nearly the same. So it says that increasing the thickness of a base layer do not much vary the tensile strain at the bottom of an asphalt layer. You can also see the difference in the vertical strain and stress here at the top of a subgrade layer. In the first case, the vertical strain at the top of a subgrade layer is 5.466 E minus 4. In the second case, it has reduced to a considerable extent. So if you increase the thickness of a base course, you can reduce the vertical compressive strain at the top of a subgrade layer. We have solved 2-layered system and 3-layered system using a Kenlayer software and understood how the thickness of different layers, modulus of different layers, or different axial configuration influences stresses and strain at critical locations. We also know now that there are at least 2 critical locations in a bituminous layer. One is at the top of a subgrade layer where the vertical compressive strain induces rutting in the subgrade layer. The second one is at the bottom of an HMA layer where the tensile strain at the bottom of an HMA layer induces fatigue damage. So these are the 2 critical locations for rutting and fatigue damage. So we also understood that axial type or axial configurations, thickness of surface layer and base layer, and modulus of 3 different layers influences these critical strains. Now we will see how if these critical stresses and strain varies when you vary these parameters. First, we will see the effect of surface layer thickness variations on the critical tensile strain and compressive strain. So critical tensile strain at the bottom of a HMA layer is considered as epsilon T. Tensile strain at bottom of HMA layer. Critical compressive strain at the top of subgrade layer is considered as epsilon C. So we are going to see how these two stresses varies for different axial loads, that is which has single wheel or with a dual wheel. And we will also see for two different thickness of base course. One is with a 4-inch thickness and other is with a 16-inch thickness. That is where you have a thin base and thick base. So with the single axial dual wheel and with the thin base and thick base system, if you vary the thickness of the surface layer, how is this tensile strain and compressive strain is going to vary with the thickness of the top surface. So that is what we are going to see now. So you have a simulation results for different cases with the modulus of E1 to be this value, E2, E3 modulus values are given here, and H1 for different depth of H1, you have a simulation results here. Let us focus on horizontal tensile strain at the bottom of an asphalt layer, which is this case. We have 4 cases here. The first one corresponds to a pavement that has a thin base of 4-inch and we use a single axial, single load configurations. The second one corresponds to a pavement with a thin base and dual wheel load. Third one corresponds to a pavement with a thick base of 16-inch thickness and single wheel. Fourth one corresponds to a thick base pavement with dual wheel. Now comparing these 4 cases, we will understand the influence of epsilon T on the thickness of asphalt layer. So we can see that there is a critical value exists for only the single wheel load cases, that is 1 and 3. So when the asphalt layer is less than 2 inch, so when you increase the asphalt layer thickness from 0 to 2 inch, you can see there is an increase in epsilon T, but this cases occurs only for a single wheel load and not for the dual wheel load. So when the thickness of asphalt layer is above 2 inch, on increasing the thickness of the asphalt layer, you can see that there is a considerable decrease in epsilon T. And you can also see that epsilon T value is lesser for a dual wheel case compared to the single wheel case. So this is as far as epsilon T is concerned. Now we can see the influence of vertical compressive strain at the top of a subgrade by varying the thickness of top surface. So here again you have 4 cases, 1, 2, 3 and 4 cases. Now the first and second case here corresponds to thin base. So you can see that increasing the thickness of asphalt layer is more effective in reducing the vertical compressive strain only if the base is thin. So you have a drastic reduction in case of 1 and 2. If you have a thick base, 3 and 4, you don't find that much of drastic reduction as in case of 1 and 2. So increasing the asphalt layer is more effective in decreasing the compressive strain at the top of a subgrade only if the base course is thin. If you provide a base course, a thick base course, H1 do not much influences. And here again you can see that epsilon C is higher consistently for a single wheel load compared to a dual wheel load. Now let us understand the effect of base layer thickness variation on epsilon T and epsilon C. So now let us focus on epsilon T first. You can see that the influence of dual wheel is pronouncing, means dual wheel have lesser tensile strain compared to the single wheel cases. And H2 increase, that is base layer thickness increase, do not have much influence in epsilon T. Just you can see the graph to be flat across different H2. So H2 increase in base layer thickness do not much influences epsilon T value. But this case, in case of epsilon C, you can see that when you increase the thickness of base layer, the vertical compressive strain drastically reduces for asphalt thickness of 2 inch. But 8 inch, you see a smaller reduction compared to 2 inch thickness. So, increasing in H2 do not influences epsilon T in much way, but it influences epsilon C, especially when you provide a thin surface when compared to the thick surface. Now, we will see the effect of base layer modulus variations in epsilon C and epsilon T. So, this is the epsilon T variation for different modulus variation of the base layer. So, this simulation was run for an even value of 2 into 10 power 5 psi and 10 power 6 psi. So, asphalt layer having a small modulus and a larger modulus with single and dual wheel. So you have 4 cases here, and thickness of an asphalt layer was kept as 4 inch and base layer thickness was kept as 8 inch for all the simulations. Now if you see the cases here, on increasing the base layer thickness, epsilon T reduces only when the asphalt modulus is lesser or 2 into 10 power 5. When you provide an asphalt layer with high modulus value, you don't see a much. Now, let us focus on the influence of subgrade modulus on ET and EC value. The analysis is run for this structure here. The structure has an asphalt layer thickness of 4 inch, base course thickness of 8 inch. The modulus of base layer is 2 into 10 power 4 psi. The analysis were run for 2 different modulus of asphalt layer. One is 2 into 10 power 5 psi and the second one is 10 power 6 psi. Also, the analysis were run for 2 different loading conditions. One is with a single wheel and second one is with a dual wheel. So, with this structure, the modulus of a surface subgrade layer is varied and epsilon T and epsilon C were determined for different cases. Now, let us focus on epsilon T values. So, epsilon T versus E3 value is nearly a flatter curve for all 4 cases. This indicates that variation in the modulus of a subgrade value do not much influences a epsilon T value. We see a quite opposite trend when we read epsilon C value here. So you can see that by increasing the E3 value, epsilon C decreases considerably and the curve is almost parallel for all cases, which says that increase in subgrade modulus value decreases epsilon C irrespective of whatever the base asphalt layer modulus is, whatever the axial configuration is. So, if you want to reduce vertical compressive strain at the top of a subgrade layer, one way is to increase the subgrade modulus. So, we have learned 2-layer system and 3-layer system analysis, and we saw what are the critical stresses and how the factors like axial configurations, thickness of a layer and modulus of a layer influences the critical stresses. Just to consolidate in short, we saw that epsilon T, which is a critical tensile strain at the bottom of an asphalt layer, is much influenced by a surface layer thickness and surface layer modulus. So, base course thickness and modulus have lesser effect on epsilon T. We also saw that vertical compressive strain on the top of a subgrade layer is much influenced by a base layer property and subgrade modulus. So let us keep this in mind when we do a design. So what next in a Kenlayer is, we will do a damage analysis, but we will come back and do a damage analysis once you learn the basic concept of damage analysis. And thank you so much for your patience listening.